Hello students, in this video we'll discuss about Miller composition technique, which is the third composition technique that we have discussed so far. Now we will begin this Miller composition technique with a caution. That is, the Miller composition technique is only applicable for systems that has two or more stages. So with that said, we'll begin with a two-stage op-amp, where the first stage is shown in magenta color, consists of transistors M1 all the way to M8, while the second stage, as shown here in cyan color, consists of transistors M9 all the way to M12. Now to this circuit, when you try to draw a line of symmetry, you could find that the left half of the circuit is identical to that of the right half of the circuit. This indicates that this circuit is symmetric. Now, to this symmetric circuit, when an antisymmetric input is applied, the tail node is basically driven to ground. Because the circuit is symmetric, let's focus only on the left half of the circuit. Recall that a pole or a zero are basically defined by this expression. So now, when a small signal Vin is applied, this creates a small signal current that flows through M1, M3 and M9 transistors. This signal path basically creates pole at node E, X and A. So before we talk about the pole locations that are encountered in the signal path, let us assume that all the transistors CGD, CDB is comparatively small in the frequency range that we are interested in. So to compute the pole location at node X, one needs the knowledge of node's capacitance and resistance. So thus, with respect to node X, we have the corresponding value of Cx and Rx as shown here. And once we have the value of the node capacitance and resistance, it becomes easy for us to evaluate the node pole, which is defined as Gm3 divided by Cx. Similarly, the pole at node E is evaluated once the node capacitance and the resistance are known, and it is being written down here. So again, one can write the pole at node E as something like this. Similarly, for pole at node A, the corresponding node capacitance and node resistance is shown here, and based on that, one can write the pole at node A as something like 1 by RA times that of CA. So one can realize that based on the values of poles, it is clear that the omega E is the most dominant pole because of the large resistance that is associated with that particular node, and omega A is the first non-dominant pole, and lastly the omega X pole exists. So the same is reflected in this frequency response plot. Note that the pole omega X is much far away from the origin, and the gain at omega X is less than 0 dB, which gives us a conclusion that it is enough to consider only this omega E and omega A poles for our further analysis. Now let's model the first stage with a block representing its gain as AV1 between the input and node E. Next, we model the second stage with another block having a gain of AV2 between node E and node A. Now, one of the most important tasks of compensation is to push this dominant pole towards origin such that we end up having a phase margin which is positive. So this positive phase margin would certainly make our system stable. Now, in order to push this particular pole omega e to this new pole location omega e prime, one needs a large capacitor at node E. But having a large capacitance at intermediate stage not only consumes a large area to realize this large capacitor, but also introduces a mismatch between the differential output nodes. So one needs a way which gives us a large capacitance but without consuming a lot of area. Now, the way to realize such a large capacitance at node A is to use this Miller capacitor Cc around the second stage, which we have already seen that this can introduce a large capacitor at node E. Now, to reevaluate the poles, let us simplify the block diagram by replacing the first stage with an equivalent Thevenin's resistance, which is denoted by Re, and the Thevenin's voltage at node E as VE. Also, one can model the second stage output impedance with the resistance value of RL, and the gain stage can be replaced with SCS amplifier. So this is the circuit topology that results after the above mentioned replacement, where the second stage is replaced with a PMOS CS amplifier, and the Miller capacitor Cc couples the input and the output node of the second stage. And the first stage is right now being replaced with this Thevenin's equivalent resistance Re and Thevenin's equivalent voltage VE. Now, let us convert this circuit topology into a small signal model to evaluate the transfer function of this circuit topology. Now, let us begin to evaluate the transfer function. So, clearly there are two nodes, and we want to write a KCL at node E, which is given as this particular expression. Next, the KCL at node A could be given by this following expression. After doing some substitution and some algebra, one can end up having an expression with first order numerator polynomial and a second order denominator polynomial. Now, let's first focus on the denominator polynomial, which I separated out from the transfer function and label it as d of s. As you could note that this d of s is a second order polynomial, means that this d of s would then represents two poles. Let me exaggerate the poles to be omega e prime and omega a prime. Note that the prime notation here denotes the new pole expressions that we end up after placing the Miller capacitor around the second stage. Also, let me assume that this omega e prime is the dominant pole due to the Miller capacitor effect at node E. So, based on this assumption, one can approximate the d of s polynomial as follows, where in the s coefficient we drop the 1 upon a prime term during this approximation. Now, comparing this s coefficient with the original s coefficient term, one would end up having the omega e prime expression to be the s coefficient term of the original d of s expression. Now, having found this omega e prime expression, next let us compare the s square coefficient with the s square coefficient of the original d of s expression. As a result, one can express the omega a prime to be as follows. Now, let's compare these pole expressions that we have derived after placing the Miller capacitance with the pole expressions that we have got before placing the CC capacitor. You could certainly note that there is a difference in the expression that we derived for the dominant pole before and after the placement of the Miller capacitance. But also note not just the dominant pole, but even the non-dominant pole expression has got changed. So due to which, let us study the behavior of both these poles with respect to the Miller capacitance. Now let's see what happens to dominant pole when the Miller capacitance value is increased. Clearly, the product of second stage gain times that of the Miller capacitance Cc becomes more profound when compared to any other terms, including the Cc times RL term. Due to which our omega E prime expression simplifies to gain of second stage times that of Cc times that of Re. Note, as the value of Cc increases further, the omega E prime moves closer to the origin. Now let's focus on our non-dominant pole expression and see what happens when the value of Cc increased. So based on the above said reason, one can strike out all other terms, leading to a much simplified expression for this omega A prime expression. Now let's learn some trick to remember this non-dominant pole expression. As shown, let me consider only the second stage in order to summarize the omega A prime expression. This is because the non-dominant pole basically happens to be due to the node A and node E alone. As we know, when the value of this Cc is increased, the impedance posed by this high value Cc becomes negligible at the frequency of non-dominant pole. This results in a circuit topology where the Ce goes in parallel with Cl capacitor, and the impedance at node A becomes 1 upon GM9 due to the diode connected M9 transistor, which is basically small compared to the resistance RL, giving an effective impedance of 1 by GM9 at node A. There are two things that one has to note here. As the value of Cc increases, the omega A prime moves away from the origin, and the omega A prime becomes completely independent of Cc. The reason for this omega A prime to move away from origin can be visualized by looking back at our omega A term, where the node A had a resistance value of Ra, but now it has become 1 by GM9. So there is certainly a reduction in the value of the node resistance at node A, due to which the omega A prime moves away from origin. Now let's summarize the behavior of both the dominant and the non-dominant pole as one tries to increase the value of Cc with respect to an S-spline. As noted in this S-spline, the cross symbol denotes the pole location when there is no Miller capacitance. But the moment one places the Cc capacitor around the second stage and starts increasing the value of Cc, both the poles move away from each other, and one can call such behavior as pole splitting. Now let us see the frequency response and see how this pole splitting behavior is superior than our previous compensation technique, where we only moved our dominant pole towards the origin. As you could note that our non-dominant pole is almost closer to omega Gx, or gain crossover frequency, making this system more stable. But there is a caution to this statement. I don't want you to take my current statement for granted, as I would disprove this particular statement while we discuss about zero. Also note that this frequency response is not a correct one. Now let's focus on 0 and try to disprove that the pole splitting actually doesn't make our system stable until one is cautious about this 0. With that said, let's look at the numerator polynomial. And we know that when the system is operated at 0, that is at omega z, the transfer function becomes 0. And this is possible only when the numerator polynomial becomes 0. So from this characteristic equation, one can obtain the expression for omega z. But note that this 0 happens to be on the right half of the S-plane, and as we had discussed in the previous lecture, that this right hand 0 induces a minus 90 degree phase shift in the phase plot. And when this Miller capacitance is increased, this omega z moves closer and closer to the origin. The same can be visualized with an S-plane along with the poles of the system. As mentioned before, the cross symbols denote the pole locations in the absence of Miller capacitance. Note that the 0 exists far away in the right half of the S-plane when there is no Miller capacitance. The moment we add the Miller capacitance, the poles move away from each other due to pole splitting, while the 0 is being pushed from higher frequency to the low frequency towards origin when the Miller capacitance value is increased. Now let's visualize the impact of the 0 in the frequency response plot. One could note that for a feedback factor of 1 at gain crossover frequency, one can find that the phase value becomes much lesser than minus 180 degree, which would make our system unstable for a feedback factor that is equal to 1. So all of this happens due to the existence of 0 on the right half of the S-plane. To avoid the 0 from coming in between the dominant and non-dominant poles, one has to understand the origin of this 0. To identify the origin of this 0, let's look at the current that flows through the Miller capacitance Cc, which can be expressed as something like this. This expression can be split into two components. First, the feed-forward current due to node potential V1. Second, the feedback current, which is IFB, due to node potential VA. Also note that when the node potential V1 is excited, it produces a small signal current at the drain of M9. When you look closer, you could observe that the feed-forward current and the drain current are functions of V1, and the sum of both these currents is what defines the output current I0. And when this I0 flows through the output impedance, it results in an output voltage V0. But as stated before, when the circuit is operated at omega z, the output current I0 or the output voltage V0 becomes 0. And this can happen only when the magnitude of both these currents are equal and opposite. That is, when both the drain current and the feed-forward current are equal and opposite in their phases. From this, one can get the same expression for the omega z. Thus, it is pretty clear that it is this feed-forward current that is responsible for the 0. So to avoid 0, one has to find a way to control this feed-forward current, and there are basically three ways by which one can control this. The first one is by making use of Nulling resistor. The second is by using voltage buffer. The third is using a common gate configuration. Out of these three methods, we will focus only on using Nulling resistor. This is the resulting block representation after placing the Nulling resistor in series with the Miller capacitance Cc. And the corresponding circuit topology is shown here. Note, the addition of Nulling resistor would actually makes the denominator polynomial of the transfer function to be third order. But since our focus is to push the 0 away from origin, let's see how this addition of Nulling resistor does this from the perspective of the node potential V1. We know that for an LTI system, we can apply superposition principle. With that said, let's analyze the output response by splitting this V1 node potential into two potentials, V1 prime and V1 double prime. First, let's analyze the output response with V1 prime while suppressing the V1 double prime potential. So this produces a drain current which is given as minus GM9 times that of V1 prime, which when flows through the parallel combination of RL and RZ with CC, it produces an output expression which is expressed as something like this. Now let's analyze the output response with V1 double prime potential alone. And one can easily evaluate the output voltage by making use of the simple voltage divider principle, and that results in an output expression as shown here. Now applying the superposition principle is nothing but it is the addition of both the responses together, which results in the following expression for the effective output voltage V0. As stated before, this V0 becomes 0 when the circuit is operated at omega z, and this can happen only when the numerator polynomial becomes 0. From this characteristic equation, one can obtain the value of omega z. Note that one would obtain the same expression for omega z when Rz becomes 0. Also note that as one increases the value of Rz, the omega z moves away from origin and goes to infinity when the value of 1 by Gm is exactly equal to Rz. And for value of Rz that is greater than this 1 by Gm would actually makes the omega z to move all the way towards the left half of the S-spline. And the same is plotted in this particular graph.